questions on pump set 17 then? Yeah.
Oh,
Pump set 17. Do you mind reading that to me? Pump set 17, number 5. Alright, I can't hear. I'm deaf and old. Go ahead. So 28.3 grams of water solid converted to liquid. That is melting, right? So it doesn't say that temperature is changing, right? What equation do we have to use? No temperature change. What equation?
moles.
Yes. Q is equal to moles times delta H of what? Fusion, because that's what melting is. So we need to take our 28.3 grams of water, 2 moles of water first, so that's times 1 mole of water over 18 grams of water, 18.02 grams of water. That gives us some number like, I don't know, 1.57. Thank you. 1.57 moles. 7 moles of water. And then take those moles of water, and you don't have to stop there. I just like to show people that you actually just now calculated moles. If you keep calculating, you can just keep on going. So take your moles of water, multiply by the molar heat of fusion, which is what for water? 6.01 kilojoules per mole to give you 9.44 kilojoules. Thank you. Any more on problem set 17? Yeah, Maitland.
Is number 4C, which is condensation, is that endothermic or exothermic?
Condensation goes from gas to liquid. Gases have a lot of energy, right? This has high kinetic energy. Liquids have lower kinetic energy. So what had to happen here? Did it gain energy or lose energy to go there? Lost energy. So that's no, it's losing energy. It's putting energy out. So heat is exiting the gas, so we can turn back to liquid. Think of it like that. It is exiting. Yes, you
so
go back.
Freezing would be exothermic.
Freezing is also exothermic. It has to put energy out from the liquid so it can turn to solid. Think about the content of energy that it's holding. Okay? Some more on problem set 17? Yeah, go for it.
Number 3, I don't have the question.
Will someone read problem 3 to me? I'm a listener. Say it again.
A small pebble is heated and placed in a foam cup calorimeter containing 25 milliliters of water at 25 degrees Celsius. The water reaches a maximum temperature of 26.4 degrees Celsius. How many joules of heat were released from the pebble?
Okay, so the water, you have 25 mils of water, that's going to be mass of water. What's the mass of that? 25 grams, because density is 1 gram per milliliter. It goes going from 25 to 26.4. So what's our delta T? 1.4, and then we know we've got delta T, we've got mass. What else do we just know? Yeah, you know the specific heat of water to be liquid water to be 4.18 joules per gram degree C. So we're going to do Q equals MCAT. So what it's saying is the pebble is hot. The pebble is releasing energy into the water in our nice little coffee cup calorimeter. So if the pebble is releasing the heat, the water is warming up. So the water has a plus Q. The pebble has a negative Q. So it's just giving you in a different way. So Q equals MCAT. Mass was 25 grams. C is 4.18 joules per gram degree C. And 1.4 degrees C was our temperature change. So 104, 105, 146. That's close. 146 joules is released from the pebble. Any more? All right, we just knocked out like 3 or 4 of our problem sets. How about let's go through thermochemical equations real fast. We've already talked about them. I just want to do the problems with you so that you don't have to do much tonight, okay? And on the other side of your lecture notes, that's why you do keep your lecture notes for a minute. We're going to talk through the first part and do some of these problems. So go ahead and do these with me. So at the very beginning, you see that you've got different equations. These equations have a delta H associated with it. What's delta H called again? Enthalpy, or heat of reaction. There's a couple names for it. So this little H with the RXN next to it is called heat of reaction, or it can be called, like for example, this one with the delta H next to it can be called enthalpy of vaporization. So you can talk about it as heat of blank, whatever the process is, or enthalpy of blank, whatever the process is. So what's the name of this one? Heat of fusion. This one, SLN means solution. Heat of solution or enthalpy of solution. So those are the names we're talking about. These VCEs tell you different things. These first two are reactions. These last ones are all just physical changes, going from gas to liquid, solid to liquid, solid to a solution, which is solution just means aqueous. So these are just physical changes. Think about this right now, as we just talked about the endo-exo part of this. Going from solid to liquid, what do you have to do? Heat it up or cool it down? Heat it up. Well, how do you heat it up? Endo or exo? Endo. You're putting energy into that solid to make it a liquid. So that's at a positive 5.6 kilojoules. Okay? Next one, gas to liquid. Okay, so cooling it down, right? Cooling it down means heat has to be released. So heat's released from that, so it's going to be exo. Yeah, exo. Okay. All right, so we just added the signs. Let's go ahead and do the problem. How much heat is gained or lost from the decomposition of 0.25 moles of sodium bicarbonate? Which of these are we looking at? The second one. Okay, so this right here is the conversion factor that we are going to use for this specific question here. So 129 kilojoules is what we're using. That is 129 kilojoules per. Notice that this is 129 kilojoules per 2 moles of the sodium bicarbonate. So that ratio, the mole ratio to the delta H that's given to you, those are now like a conversion factor in themselves. So I'm going to write it just like that. That per 2 moles of sodium bicarbonate is what we're talking about. All right, so that's just a conversion factor. Very first thing you're starting with is the fact. What is the fact? Yes. Okay, what's up, Hannah?
You're the minus
Mm-hmm.
ours says H con. Is that
Minus at the top. Where do you see that?
where you put the minus on?
Oh, okay, yeah, because it's actually condensation, because it's going from gas to liquid. So that's what I'm saying. So I wrote that because we already talked about this. We talked about how delta H of condensation, the numerical number 40.7 is the same, but the sign changes. So vaporization is going from liquid to gas, right? So we're putting energy into that. Vaporization is a positive number. The condensation one is the negative number. So I think I was just going to reinforce that, but we already had talked about the numbers being the same, it's just the signs were different for the opposite process. All right, so back here, we're starting off with the 0.25 moles of the sodium bicarbonate. I want to figure out how much heat. So what unit am I looking for? What unit? I'm looking for kilojoules. So all I'm doing is taking what I have, using my conversion factor. So I'm just going to multiply by this conversion factor, but how do I write it? Do I write like that, or do I flip it? Right, because I didn't want to cancel the 2 moles down here. So 129 kilojoules goes down here. 2 moles of the sodium bicarbonate goes down here. Moles and moles cancel. Yay. And I'm 2 kilojoules. I'm 2 joules. I'm done. I'm going to figure out how much that is. Looking at my handy dandy. That's divided by 2. I don't have that final for some reason. 16.1 kilojoules sounds great. Okay, that's not so hard. It's just reading and using the correct conversion factor. Next one, how many grams of liquid water will be formed from the addition or removal of 456 kilojoules of heat? I just want to double check that. That times. Awesome. Okay. So now we're looking for grams, right? So question mark is how many grams of liquid water, so water, will be formed from the addition of 456 kilojoules of heat. So what's my starting point? Right, so 456.0 kilojoules of heat. I I need to multiply that by something. What do I need to get rid of right now? What unit? Okay, so where do I go look for that? The top, yes. Okay, so water. Which one's water? This one right here. I have 40.7 kilojoules of heat. That is being, added or removed if you're going from liquid to gas or gas to liquid. So 470 kilojoules per, you see there's a 1 right there and a 1 right there? It's per 1 mole then. So our new conversion factor for this is 40.7 kilojoules per 1 mole. So I'm going to use that. Down here, and then we'll do molar mass. So the kilojoules, because it has to go on the bottom, so 40.7 kilojoules has to go on the bottom. 1 mole of water has to go on top. And it says how many grams, so we got to go one more step to molar mass. 1 mole of water, it is 18.02 grams of water. Anybody? 201.6 grams of water. Everything cancels except for grams. So you just have to search for the correct unit, look at the question, search for the correct delta H first, and then see how you're going to implement that new conversion factor. You just read off of the BCE and the number next to it. Let's do one more. Sounds great. Okay, how much heat is released or absorbed by dissolving 42.3 grams of sodium hydroxide in water? And then, how much would this amount of heat change the temperature of 1 liter of water? So we have a two-part question here. How much heat is first and we're looking for, right? So what are we looking for? What unit? Looking for kilojoules, right? Or joules here. So there's our kilojoules we're looking for. We're starting off with what? 2.3 grams of sodium hydroxide. So let's go back up to the top and see which one's relevant. Okay, so this one right here. So the solution process is going to feel hot, right? It's going to put out 445.1 kilojoules per what? How do you know? 1 mole, 2 moles, what? Right, because the coefficient is 1 here. So that's going to give us that conversion factor, 445.1 per 1 mole of sodium hydroxide. So let me write that down. Yes, it is negative. So we're going to talk about it being released. Okay, 441, what was it? 445.1 kilojoules per 1 mole is that conversion factor. Okay, and it's released because of the negative sign. All right, so what do I need to do first to this? Right, so 1 mole of sodium hydroxide, so like, so 24, so 40. 40 grams of sodium hydroxide is what the molar mass of that is. That cancels, that cancels. Last step is to convert to kilojoules. So 445 or 445.1 kilojoules per 1 mole. The moles cancel. That gives us 470.69. I didn't write that right. 0.69 kilojoules of heat are released. 470.69 kilojoules of heat is released. What was the second part of the question?
How much?
That question there. But what do we need to do? What do you guys think?
How would you plug it in?
Yes, we're going to plug that Q into CubeSumCat. So, sorry, this is weird. All right, so taking the Q we just got of 470, we're getting skills diminished when I'm in my theater outfit here. Okay, so that's how many kilojoules we have. We need to change that to joules though. Why? Yeah, because C has joules in it, so we need to convert it appropriately. Can you do that in your head? Y times 1,000. Right, so in your head you're going, I got 1,000 joules and 1 kilojoule, so kilojoules cancel. So that is, with that 470,690 joules is equal to MCAT. Well, what's M in MCAT here? In this question. No, that's grams of water. It's asking for that, how much would that amount of heat change the temperature of 1 liter of water? 1,000 milliliters, so it's 1,000 grams because of the density of water being 1. So 1,000 grams. What's C? 4.18 units per gram degree C, right? And then what's the temperature change? Oh, how much would this heat change? I don't know. Let's calculate. All right, so 400, that number, divided by 1,000 times 400, or 4.18. That would be, I got you, delta T is 112.5 degrees C. So I just divided. I just said 470,000 something divided by 4,018 or 180. 4,180. You guys can tell it's algebra. All right, look through the rest of them. Tell me if you're okay with those, so you can do those later at the end of class. I think there's 4 more. Standard heat formation. Where's the other question?
The last one, 6.
Oh, I did. That's one of these with the. Well, I don't know if I want to teach this right now. Do I teach this right now?
No.
Okay. Let's do. You guys are doing 4 and 5. That's the only thing I'm not teaching. That's AP. That's the small stuff. You can work to your AP with me. Okay. Let me take it to the lab, and then you guys can do your homework at the end of class. We are going to prove what the heat of fusion of water is. What do we think the heat of fusion of water is? 4. Heat of fusion of water. 6.01 mole. I need you to verify that in the lab. So, what are you going to be doing to water today?
Oh wait, and melting it.
You're going to be melting it, okay? So I'm going to give you solid water, okay? I'm going to give you solid water, people. And then you are going to confirm the heat of fusion. Okay? So, let me tell you what this looks like in the lab so you can find it. Oops, that's not it. Oops, no. Heat of fusion. Yeah, they are burning a peanut. It's a different lab. Okay, so listen. I don't know what picture is. It's gone right now. You do need to read through. I'll just wait. You good? Okay, cool. You need to read through the very beginning so that you understand how the calorimetry part is going to work. It just talks a little bit about here. And it goes through, it shows you Q equals MCAT again. You guys are probably very good at that now. But you do need to read through these instructions because I need you to get these temperatures directly as they've stated here. And then your data collecting. So you're going to show your volumes, your temperatures, and so forth. Mass of volume 2. This is very specific because I want you to verify. And the ones who get the closest, I might consider more money in. And I do have to give you more money for your substitute for staying with Miss Fur very, very nicely too. Okay? The guy from what? Oh man. I guess someone have to. Yeah, I gotta get on this. Okay, so I will let you guys. Let me go ahead and display. I cleaned up the lab a lot yesterday. I had to get paid $30,000 a year. We got time for that. I will prep every lab for you anytime, but I'm not going to clean up your mess. So if you don't have enough time to end class, then you need to stay for 2 minutes and finish cleaning up. Thank you for those of you who do clean up. I appreciate it. It takes a lot of time to prep these labs to make sure we're good here. So I've already got bowls at your desk, and I have the cooler back there with the ice in it. I'll come to you and distribute some ice to you. But you probably want to get going because the ice is going to start melting. You want some fresh ice. Solid water. And you need to choose different groups today. Some of us work really well together, but some of us don't. So I'm trying to get you guys to choose different groups you think can be a good lab night. So 4Zs are at the big stations, and then 3Zs are at every other station. So
Is that just completely different?
a little different. A little different.